Well, there's really three different types of uh, protein or enzyme inhibition. There's competitive inhibition, uncompetitive, and mixed or non-competitive inhibition. The best way to really kind of grasp this or put it in like a equational form is use this equation. So right here we have the enzyme. E plus S is when the substrate binds to the enzyme. And then here, this is the sign for the binding of the enzyme to the substrate. So then right here is the enzyme substrate complex. And then this arrow right here represents the catalyst, or the reaction basically. So then the enzyme stays the same and unchanged, and then the product leaves the enzyme, and the enzyme goes back here, and then whatever. So whatever the body needs, that's what the enzyme does. So let's look at competitive inhibition first. If we're going to use this method of kind of describing it, what we would do is we would first write down, E plus S, and then once that binds, we have the ES here, and then we're going to let it go to E plus P. So that's how it would normally go without an inhibitor. But since it's going to be competitive inhibitor, what it does is the inhibitor binds to the enzyme. So before it could continue with this reaction, this inhibitor creates this enzyme inhibitor complex, making it so no product can be formed, or no substrate can actually bind to the enzyme. The graph of this is actually really simple. It would look kind of like this and this. So this is what's called a double reciprocal plot or a Lineweaver-Burk plot. It's basically your y-axis is 1 over the v naught, and then your x-axis is 1 over the concentration of substrate. Right. And it's really nice because each inhibitor makes the graph look different, or it changes the graph in a certain way. So let's say we had a control right here. Let's say this is our control, and then let's get another color. Why don't we to have the enzyme with the inhibitor? So with the inhibitor, what you're going to see is it's going to have the same Vmax, but different Km values. So that's how you know it's going to be a competitive inhibitor, is if the one half Vmax is the same, and the Km values are different. So let's see, here's the 1 divided by, that's not what I wanted. So negative 1 divided by Km is this one. That one right there, and then 1/2 of the Vmax. Okay, anyway, is that value right there. Another way to look at this is you can say that it prevents the substrate from binding. That's what a competitive inhibitor does. And so if we notice what happened here, the Vmax didn't change really. So we say that's about equal. But the Km value, on the other hand, Km value it actually increased. You see, it got less negative, but really it's not negative because just the nature of this plot. So the Km increases. So that's all you really need to know about competitive inhibitors. So the inhibitor binds to the enzyme, which prevents the enzyme or the substrate from binding to the enzyme. So then it just has this inactive enzyme inhibitor complex. And this is what the Lineweaver-Burke plot looks like for a competitive inhibitor. Now for the uncompetitive inhibitor, we'll have the same thing right there, and then paste. Awesome. Alright, so we have the same equation without an inhibitor, but for an uncompetitive inhibitor, the inhibition actually happens at the enzyme substrate complex. So let's see if I can. Okay. So that's going to go boom, boom. And then you're going to create an enzyme substrate inhibitor complex. And then that will make it so then it cannot make a product. So no product can be made as long as the inhibitor is on here. So I guess if you wanted to say that with words, basically a non-competitive inhibitor prevents catalysis. Alright. And then the Lineweaver-Burke plot for this thing would look like this. So obviously we have 1 over V naught, and then 1 over the concentration of the substrate. This graph looks slightly different in the fact that the control, or the enzyme without an inhibitor, that doesn't change because there's no inhibitor. And then once an inhibitor is added, the shift, it gets shifted this way, so like this. And you'll notice that these lines are parallel. So if you see a graph like this, and the lines are parallel, that means it is an uncompetitive inhibitor. With this, what happens to here, so right here's the control. So here, and then this is the control. And then this one right here is this enzyme substrate inhibitor complex. So what happens here is the Vmax of the reaction goes down, and the Km value goes down. So I know it's kind of counterintuitive. If the graph is shift up, then how are these values going down? Well, this is an inverse graph, so nothing's really negative on this graph. It's just that biochemists don't like unstraight lines. They love the straight lines. It's easier to calculate things out of these graphs than with an asymptote or like a type of sigmoidal curve. So it's much easier to calculate the Km, the Vmax, and honestly, to see what kind of inhibitor is going on. So you can tell that just by looking at these graphs that different inhibitions are going on. And now let's get to our last one, which is the mixed / non-competitive inhibition. Okay. This here. Okay. So what happens here is there's 2 different binding sites on the enzyme. So, you see how there's only one different binding site? With mixed non-competitive, something binds here to create enzyme inhibitor complex, or it's going to bind to the enzyme substrate complex and create an enzyme substrate inhibitor complex. Alright. So what happens with this Langley-Burt graph? So here's V naught. Here's 1 over the substrate concentration. If we're going to have the control be right here, let's say, then our inhibited one is going to look like this. So they have the same Km value, but differing what's called a Km value, or Kd, basically binding affinity. So if we look at this for a mixed reaction, or a mixed / non-competitive inhibitor, the Vmax goes down, is lowered, and then the Km value stays the same. And we can see that, like, even though, like I said before, even though we shifted this up, since it is an inverse graph, shifting up means the value is getting lower, if that makes sense. Couple other things to note. So binding of a substrate is inversely proportional to the Km value, and the binding of the substrate is proportional to the Vmax. So in other words, if the Km is high, the Km value, then the binding affinity is going to be really low, and inversely, if the Km is low, then the binding affinity is really high. But if the binding of the substrate is also the binding of the substrate is proportional to the Vmax, so that means high Vmax, high binding affinity, low Vmax, low binding affinity. And I don't know if you've gone over double reciprocal plots yet, but yeah, it's the best way to figure out Vmax, Km, and a type of inhibitor, because everything is just apparent. Like, the y-intercept values are the Vmax, and then the x-intercept value is the Km value. So hopefully this helps you a little bit with your competitive and non-competitive questions. I'm going to work on another video right now, so then you can have a video for your question about 5D.